So the mathematical definition that I gave you for a second order tensor, based on that understanding, whatever is coming out from that definition, now I want to make an attempt to express a second order tensor using a Cartesian coordinate system. So suppose I have this Cartesian coordinate system. Okay. The origin of the coordinate system is at Q, and E1, E2, E3 are the basis unit vectors. If I want to write the name of this coordinate system using our notation, what will that be? It will be like this. This is the coordinate system I am referring to. I have said earlier that if I write or describe a coordinate system like this, the first letter, the first alphabet here is the origin of the coordinate system, and then these three are the basis unit vectors, right? And then these three characters, they are the coordinates of a general point or a typical point P in space. Right, so if I have a point P here, its Cartesian coordinates would be x1, x2, x3. Those are the characters that appear here. I want to express a second order tensor using this Cartesian coordinate system. Before I do that, let's remind ourselves how would we express a vector using this Cartesian coordinate system. So if V is a vector, which by the way is a first order tensor, how do we express this? Now since a vector is a first order tensor, according to the definition or the description that I shared on the previous slide, how many scalar components will it have? It will have 3 raised to the power 1 equals 3 scalar components. We are very familiar with this fact. Even though we are familiar with this fact, my interest is here to show you that this familiar fact about vectors is also covered by the definition or the description of a tensor of order n that I shared with you. Okay, 3 scalar components. So if I choose to express this vector in this coordinate system, it will be written as something like this. Right, where v1, v2, v3 are the scalar components of V along E1, E2, E3. Unit vectors. Now suppose somebody else enters the room and he says that I do not want to have this coordinate system as my working coordinate system. I want to have a different coordinate system, like what I am going to draw now. Still the three directions are mutually perpendicular. He is also using an orthogonal coordinate system. However, he has chosen the unit vectors to be what I am writing now. So if I want to give a name to his coordinate system following the notation what I have here, what will be the other coordinate system? The other Cartesian coordinate system will be written as q x1 prime e1 prime x2 prime e2 prime x3 prime e3 prime, where the basis unit vectors are now all primed, and in general we are saying that E1 is not the same as E1 prime. That's why I use this superscript prime to say that these are different. Okay. And similarly, this point P will now have its coordinates as this. Point P is the same. It's the same point P, but it will have different set of coordinates because now the working coordinate system itself has changed. Right? Since he has chosen this coordinate system as his working coordinate system, how will he express the same vector v? How will he express the same vector v? For him, the vector v will be written as v1 prime e1 prime. v2 prime e2 prime and v3 prime e3 prime. This is the second coordinate system, and the second coordinate system is the working coordinate system. Okay, and when the first coordinate system, the white one, was the working coordinate system, this is the expression we have. Same vector, two expressions. The vector remains the same. Why would the vector depend on the coordinate system? Right? However, scalar components have changed. In general, v1 is not the same as v1 prime. Right? In general. These facts we are already aware of. I know you are aware of. Why I am going over these aspects of vectors? It is because I want to tell you that whatever you know about vectors, they are in line with whatever is there. This text matter is talking about tensor of order n. So based on our familiarity of the properties of tensor of order 1, that is vector, I want to now talk about tensors of order 2. Alright. So if I have a tensor of order 2, Now the question is, how do I express that tensor? Okay. Tensor of order 2 will have 3 raised to the power 2, which is 9 scalar components. For a given, in a given coordinate system. In another coordinate system, it will still have 9 components. However, those 9 components will be different. Will in general be different. Nine components in the second coordinate system. बोलो थोड़ी देर. Okay. 9 scalar components will be different. Redrawing the first coordinate system. If I have a tensor of second order, that will be expressed in this coordinate system as just 1 minute. Talking about expressing this tensor, second order tensor, in this coordinate system. This will be expressed as where these 9 numbers, the 9 quantities, scalar quantities that I am writing here, these are 9 scalar components of the second order tensor T in the shown coordinate system. So this scalar, various scalars, they are coming with two indices, right? Two indices. And those two indices tell us that which scalar component that particular Tij is. For example, if you have Tij like this will be called the ijth component of tensor T in the shown coordinate system. Okay. Now note that T12 is not the same as T21. Order matters. Further, observe these quantities here. Perhaps this is the first time you are seeing a quantity like this. So I am putting two unit vectors side by side, and these unit vectors, there is no dot product, there is no cross product. It's a new type of product, I must say. This is a new type of product, new type of vector product. So the moment you start talking about a second order tensor, you will have to define a new type of vector product. You have EI coming first, EJ coming second. Now note that in this manner, if you look at this quantity, this product, note that this is not the same as this. Order matters here. Such a product is called a dyad. So to be able to express a second order tensor in this coordinate system, we first need to define these dyads, and there are 9 of them, right? It will be E1, 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 E2, like this, all the way to E3, E3. So you define first 9 dyads, and then you use those dyads here, multiply them by the corresponding scalar components T11, T12, T13, and then you add them up all together. That is the full expression for tensor T. Now if you change the coordinate system like I had on the previous slide, if somebody comes and says that he would like to have the yellow coordinate system as his working coordinate system, then what happened? The expression for V changed, right? In the yellow coordinate system, you wrote the tensor, you wrote the vector like this. In the original white coordinate system, you wrote the vector like this. Similarly, if somebody is changing the coordinate system, to again like this, with all primed quantities, and you want to express the same T in this coordinate system now, that will be T11 E1 E1 prime prime prime. Nine such terms finally you will have. I can write it in a compact form as this. Double summation. I goes from 1 to 3, j goes from 1 to 3. That's T in the yellow coordinate system. From the previous slide, if we go back to our white coordinate system, the original one, the expression will be this. Okay. And in general, Tij is not the same as T prime ij, and in general Ei Ej is not the same dyad as Ei prime Ej prime. Okay. So with this understanding that a second order tensor requires these 9 scalar components and 9 dyads for their full expression, now let's come back to the problem we had earlier. I want to express the angular momentum of body about point A as something which is a second order tensor, a dot product, and then the angular velocity of the body. So if I make now a coordinate system which is this. Okay, so let's use as our working coordinate system. Note that A is a point fixed in M. Okay. Now A is also the origin of A. Mind you, A is the same point about which I want to compute the angular momentum, and A is also the point which is the origin of this coordinate system. And of course frame F is there. I am not imposing any restriction on E1, E2 and E3. I am not saying may or may not be fixed to M. I can have such a Cartesian coordinate system. Earlier when I talked about 3 different types of coordinate system, I was saying that my Cartesian coordinate system was frame fixed. I used to fix it here, F. And when I say I used to fix it in F, the origin of the coordinate system was fixed to F, as well as the unit vectors were fixed to F. However, here I am talking about a totally different coordinate system. It is Cartesian, but its origin is now A, which is a point fixed on the RB itself, and I am not putting any restriction on E1, E2, E3. Right now there is no restriction required. Okay. Now suppose HAF the vector HAF is written in this coordinate system as right. I can always express HAF as H1 E1, H2 E2 and H3 E3, where H1, H2 and H3 are scalar components of HAF along E1, E2, E3. Omega MF, let us write that as omega 1 E1, omega E2, omega E3. Alright. Now I just realized that I should have put a double bar here because it's a second order tensor here and here. Now IA is going to be expressed as this. Now mind you, so far I have not clearly defined what IA itself is, neither physically nor mathematically, but I am treating that as a second order tensor. Alright, and since I am treating it as a second order tensor, after all its expression in this given coordinate system will be this. I mean, I'm just using IA11 as the scalar components, so it should be written in this manner. First three components, then I will have IA21 write it in a more ordered manner. I want to write from here. It will be IA11 E1 E1, IA12 right, first three, then E2 E2 IA23 E2 E3. Plus three more terms, IA31 E3 E1, IA32 E33 E3 E3. Okay. Now let's take this full expression of I from here and the expression of omega MF from here and do the dot product, right? Because my claim is that HAF is a dot product between a second order tensor and a vector. Okay. Now, whenever there is a dot product, so far we have seen that if E1 is dotting with E2, we are familiar with a vector, a unit vector dotting with another unit vector. What will this be? This will be 0. If E1 is dotting with E3, this should be 0. They are mutually perpendicular unit vectors. However, if E1 is dotting with E1, that would be 1, and so on. So we will keep this fact in mind that two unit vectors, if I have three mutually perpendicular unit vectors, the dot products will be 0 unless both the unit vectors are the same. Otherwise all will be 0. The second thing that we want to keep in mind is that if you are having a dot product like say IA13 E1 E3, and this is supposed to dot with suppose M3 omega 3 E3. Suppose you come across a term like this. This unit vector with what? Whether it will dot with this or whether it will dot with this. Earlier when we used to see only two vectors having dot product, there was no ambiguity. Of course E1 will dot with E3 and in this case it will be 0, or E3 is dotting with E3 and this will give me 1. But now you will have a situation in which from the left hand side a dyad is coming. So a dyad is going to dot with a unit vector. How do we handle this? The rule is, we are making a rule now because it's the first time we are coming across a situation like this. The rule is that the rightmost unit vector of the dyad undergoes dot product operation with the unit vector appearing on the right hand side, the RHS of the dot operator. This is the rule. And thus, if you come across a term like IA13 E1 dot E3, not dot, E1 E3 dotting with something like omega 3 E3, what we have to do? We have to take dot product of these two. And what will this do? This will survive. This will just remain there. This will just remain there. And thus, this will be IA13 E1 omega 3 E3 dot with E3. In this case, it will be, this will be just 1. You can write that as omega 3 IA13 E1. Okay, this is how the dot product will happen. Now, if you go back to this long expression where I had these 9 terms and there are 3 terms here, you put them here and take dot product, you will have 27 such dot products appearing. 9 terms from here, 9 terms from IA, 3 from here, 27 terms. But several of them will be 0. Why? Because you will come across situations like this. Out of 27, what will happen? Only 9 will survive. And those 9 I am going to write here. Okay, this is the vector equation in my Cartesian coordinate system. What will happen is left hand side will be written like this, which is straightforward, and right hand side, after you have performed all the dot operations, 27 of them, only 9 will survive, and those 9 will be those 9 will be those 9 terms will be, I just want to make sure that I am writing the indices correctly because I am not deriving it fully right now. Ij, omega j, yes, I have written it correctly. 1 1 I 1 1 I j omega j. One 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 omega j internally. Yes. First 3 terms are this. Then you will have 2 1 omega 1 E2, 2 omega 2 E2, 2 3 omega 3 E3, 3 1 omega 1 E3, 3 2 omega 2 E3, IA 3 3 omega 3 E3. 9 components. One 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 one. One 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 one, 2 2 2 2 2 2, 3 3 3 3 3 3, 1 1 1 2, 1 1 2 2 3 3, 1 1 2 2 3 3, 2 2 3 3. Yes, I believe it is correct. This can be written in compact form as IA IJ omega j EI. I goes from 1 to 3 and j goes from 1 to 3. So if you compare this here and this here, it means that H1 is IA11 omega 1, IA12 omega 2, IA13 omega 3 can also be inferred from here actually. IA11 omega 1, IA12 omega 2, IA13 omega 3. Okay, and H2 will be IA21 omega 1, I know it is right now very mathematical and I do not know any other better way to introduce this, but at least I can assure you, once I have completed the mathematical expression, I will make an effort to explain the physical meaning of this also to the best of my ability. So for the time being, please try to pay as much attention as you can to the mathematics. As I said, there is no other way that I know how to introduce it without all this mathematics. Okay, Hi j omega j. Okay. Now these are three scalar equations. These are all scalar equations. Three scalar equations that I have extracted out of that vector equation. Now if you pay attention to these three scalar equations, you will realize that it is possible to express this in a more compact manner in a matrix form. In a matrix form. So on the left hand side I have a 3 times 1 matrix, 3 rows, 1 column. On the right hand side, this term, this factor again is a 3 times 1 matrix. And as you are aware that if this is 3 times 1, this is 3 times 1, this has to be a square matrix of 3 times 3. And now let's try to fill up the blanks here in this 3 by 3 matrix looking at these three equations. I think the first element here of this matrix should be IA11. This should be IA12. This should be IA13. See this equation? IA11 omega 1, IA12 omega 2, right? And this second row in this matrix would be and the third would be, which is coming from the third equation here, would be this. Okay. Now symbolically we will refer to this equation. So this I will write here 3 times 1 matrix, 3 times 3 and 3 times 1 matrix. Symbolically I will write this equation now onwards as H AI the matrix version of the vector HAI, and this I will refer as IA, and this I will refer as omega MF. To be consistent, let's put here double bar. So what was appearing as a dot product in terms of the vectors and the tensors themselves, once I have used a Cartesian coordinate system as my working coordinate system, that appears as a matrix equation, where the definition of this matrix, this is simply this H1, H2, H3 column. Definition of this matrix is this 3 by 3 matrix. I mean 3 by 3 matrix, and the third one is omega MF matrix is this column matrix. Okay. I've already covered this. Maybe I'll just write here again. No, this is I here. This should be F, because I'm talking about HAF. Right? This is still the frame is F. Made more mistakes here. This is also F. Here it is okay. Okay. No, the framing context is still F. So this is the matrix form. We will call this matrix as the inertia matrix of RB about point at point A and relative to coordinate system that's what we will call. So mind you, if I write this, I call that as inertia tensor of RB at point A. This is the full tensor, and a tensor is independent of the coordinate system. It's just like you say that velocity of a particle p with respect to f is denoted by this symbol. So this is the velocity vector, right, of p with respect to f. Similarly, with 2 under bars, I say it is inertia tensor of RB at point A. However, when I put IA within square brackets, it is called inertia matrix of RB at point A relative to coordinate system. So the moment you put square brackets here, now you are talking about a set of 9 numbers, 9 scalar components. And you know that by this time that scalar components of a second order tensor will always be cast or will be represented using a coordinate system in the background. And thus I also need to specify this inertia matrix of RB at point A relative to coordinate system, this long coordinate system. Oh really? Okay, we stop here. Alright, so tomorrow we will have tutorial. I will be there in the classroom. Yes, please, Rishabh, you may disconnect.